Hello everybody, and welcome back to another video on my channel. Today, we will be talking about some miscellaneous calculus. Basically, what this is going to be is a few of the videos that didn't make my official guide, or just general topics that aren't like super confined to one thing, but they really teach a lot about calculus as a whole, and serve as a really good conjunction to a lot of the main material. These things include interesting problems, or just topics that are not normally covered or not normally part of calculus. So, that will be a compilation of those videos. Thank you so much, and let's move on to the first one. The Putnam exam, the 1968 one, which A1, it says, prove the integral from 0 to 1 of x to the fourth times 1 minus x to the fourth over x squared dx is equal to 22 over 7 minus pi. Now, number one, essentially all this problem asks you is to evaluate this integral, which we will do, and now proving that 22 over 7 is greater than pi takes one small extra step, and that is proving that this integral is positive. Now, how will we prove that this is positive? Well, first, let's draw a coordinate plane. Now we have our x and y axis over here. Now, of course, there's also the negative over here and over here, but we're not going to worry about negative x, but it's essentially the same thing. Now, if I have a function like this, and then this, and then this. Now, this is a very weird function, yes, but the point is not that. The point is this area, which is above the x-axis, contributes positive terms to the integral. But this area, which is underneath the x-axis, produces negative terms to the integral. So, if the integral from this region was positive, we would have to show that this function is positive for all x between 0 and 1. So then you would know that if the y is positive, that means this area over here has to be positive. So let's show that this function is positive. And sorry, it's not x squared, it's 1 plus x squared. Now, so we have 1 plus x squared, and for all real numbers, that's positive. As for all real numbers, x squared is positive. So that's the denominator. Now, over here, sorry, oh my, I wrote this wrong again. 1 minus x to the power of 4, all of it. And now over here, we have something to the power of 4, which is again just something squared, so that has to be positive, times another positive number, since the power of 4 is positive. So we have a positive term divided by a positive term. And that becomes another positive term. So we know that this function is going to be positive for all real x. So it will obviously be positive for a small slice of that real x. So now let's move on to evaluating the integral. So we start by evaluating the numerator. So we have the integral from 0 to 1 of x to the fourth times 1 minus 2x plus x squared divided by 1 plus x squared dx. Now this becomes the integral from 0 to 1 of x to the fourth. Now squaring this gets us x to the fourth. And then after that, if we just do multiplication like this, we get x squared minus 2x plus 1, and then minus 2x plus 4x squared minus 2x cubed. And then after that, we get x squared minus 2x cubed. And then we obviously know over here is x to the fourth. So, evaluating all of this gives us 1 minus 4x plus 1. Then we have x squared, and 4x squared, so 6x squared. Then minus 4x cubed over here, and then x to the fourth. Now, if you knew about the binomial theorem and Pascal's triangle, you could have also just evaluated it using Pascal's triangle. So 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and this would be the row that you needed. But I haven't covered Pascal's triangle yet. I feel like that belongs more in number theory, which will be a topic I cover after this. So that's that. Now multiplying that, or just first putting it in this expression, x cubed plus 6x squared minus 4x plus 1 over 1 plus x squared dx. So now that we have that, we can just multiply it out. Integral from 0 to 1, x to the 8th minus 4x to the 7th plus 6x to the 4th minus 4x to the 5th plus x to the 4th. And all of this over 1 plus x squared and multiplied by dx. So there's that. But what do we do now? We've already exhausted all our options and there's not really any smart substitutions. So why not we just evaluate it? Why not we just divide this polynomial? We can do all of this huge polynomial divided by 1 plus x squared, and maybe we'll get something good. So let's divide some polynomials. So first, let's set up our equation. We have 1 plus x squared, and then over here, sorry, let me draw a better line. That was a really bad line. Let me set it up and show you. All right. Over here, we have this entire polynomial, and we're essentially just going to perform long division on this polynomial. Now, if you're not sure what this is, I recommend checking out my video in the algebra series that covers division, or you can also look at other videos online that cover this. And since we are in a calculus series, I assume you know all these skills in algebra, but if you don't, that's perfectly okay. You can just go and review and come back to this. So let's start the process. X to the 8th divided by x squared is x to the 6th. So then you have x to the 8th plus x to the 6th. And then you have to flip the signs as we do in long division. So we do this, minus, minus, and we go again. So over here is this x to the 6th is not there, but it does get transferred over here, and the negative 4x to the 7th does get transferred down. So negative 4x to the 7th plus 5x to the 6th. And let's continue solving this problem. 4x to the 7th plus negative 4x to the 7th becomes negative 4x to the 5th. So negative 4x to the 7th minus, now we'll bring down this extra term because we need it, but we'll remember not to bring down any more. So minus 0 minus 4x to the 5th, and then we just flip the signs. This goes away, this goes away, this goes away, so we get 5x to the 6th. But you see over here, this cancels out perfectly. So we run this over here, and there you have it. So since that also worked, we just left with 5x to the 6th. Now we'll add in x to the 4th, and I said earlier I wouldn't, but these canceled out, and we do need another term to divide by. So this becomes plus 5x to the 4th, so 5x to the 6th, and then plus then 5x to the 4th over here, and then we of course subtract it. So we flip the signs on this, minus, minus, this gets canceled out, and we are left with negative 4x to the 4th, and there's really nothing else to pull down. So we continue. What we have here is negative 4x to the 4th, so we get negative 4x squared, then we get negative 4x to the 4th, minus 4x squared. So after we flip signs, this becomes the same thing, 4x squared. So what we have is this becomes plus 4, 4x squared plus 4. But then, of course, you have to flip the signs. This cancels out, and we are left with minus 4 as our remainder. So then by the remainder theorem, what we can just do is we can just say minus 4 over x squared plus 1. And that's really about it. And we have just found what we needed to find for our long division. So now that our long division is done, we can go back to actually solving the integral and not just evaluating algebra. So going back to the integral, we can just put the polynomial stuff in one term. So the integral from 0 to 1 of x to the 6th minus 4x to the 5 plus 5x to the 4th minus 4x squared plus 4 dx, and then minus integral from 0 to 1 of 4 times the integral of 1 plus x squared over 1 dx. Now, if anyone remembers the inverse trig integrals, this one becomes arctan of x from 0 to 1. So over here, that's arctan of x, and we just integrate this like a regular polynomial. So what we get is x to the 7 by 7 minus 2x to the 6 by 3, and then plus x to the 5th minus 4 by 3x cubed plus 4x from 0 to 1. And then after that, what happens is we have just minus 4 times tan inverse of x from 0 to 1. And let's start again over here, creating boundaries. This is not the easiest integral, but it is still very achievable. We get, by substituting 1, 0 makes everything 0, so we'll just substitute 1 for the first time. We have 1 by 7 minus, then we have 2 by 3 plus 1 minus 4 by 3 plus 4. Now this becomes minus 2, and then minus 2 plus 1 is minus 1, plus 4 is 3, and 3 plus 1 by 7 is equal to 22 divided by 7. And in a similar way, tan inverse of 1 minus tan inverse of 0 becomes then pi over 4. And the reason is tan inverse of 0, basically tan of what is 0. So tan of, let's say, x is equal to 0. That means since tan is sine by cosine, you can have sine of x equals 0, and that happens at 0. So that's that part. And since tan of x would need to be equal to 1 in this case, and that comes at pi by 4. So we get pi by 4. But we forgot to multiply by 4. So this equals pi. So now we know what the two parts of our integral are. We can go and say 22 over 7 minus pi is the answer to our integral. And since this is a positive number, 22 by 7 minus pi is greater than 0. That means 22 by 7 is greater than pi. And that is our second thing proven. But what do differential equations even mean? Basically, those are equations that involve derivatives. So let's say I have the derivative of a function squared is equal to x squared. This is a differential equation, as this involves a derivative. And since not just a derivative, this involves the square of a derivative, or essentially like using a derivative as a function, as the derivative of a function as another function. Now, what will we do to solve this? Well, we'll take the square root of both sides, so dy by dx is equal to x, and then integrating both sides, we get x squared by 2 plus c is equal to y, and that's our answer. We have our function over here. But what if we have multiple derivatives and other stuff? Well, then those require many different techniques. But today, we will not be talking about those. Today, we will be doing a quick introduction, so basically classifying them, and also covering one small technique called solving a differential equation by separation, or separation of variables. So, without further ado, let's move on to those methods. Well, the first thing that we need to do with any new topic is classify it. There are different levels of differential equations. There is many ways to classify them. There are two main types of differential equations: ordinary differential equations and partial differential equations. Now, ordinary is just regular derivatives, like the one over here. Now, partial differential equations have partial derivatives, but this is covered in multivariable calculus, so we will not be covering this for today. Will not be covering. So, how else can we classify these? Well, let's look at the derivative. As we see, we have the first derivative. So, we can say this is of order or degree 1. Order or degree 1. And let's say we had a second derivative or a third derivative, that would be order of degree 2 or 3. And that is kind of like classifying a polynomial. Like, ooh, that's cool. Why not we classify just like a polynomial? And since we just did that over here, it becomes very easy to actually understand. So that's the next way to classify. How many derivatives are being taken? Alright, now we know that. But how other ways can we classify it? Well, we could think, what are we doing to those derivatives in the equation? As you can see here, we're squaring this derivative, so it would not be a linear equation, just like if this was a variable, as you're squaring it. So we could classify it as linear/nonlinear. That's another way to classify this equation, linear or nonlinear. And those are basically the main ways to classify an equation. Now there are others like homogeneous and heterogeneous, I think, or non-homogeneous, and there's also other stuff with the coefficients, but those would be taken in the actual differential equations course instead of actually learning how to classify it, and those are more advanced. So this is really all you need to know for now, whether it's ordinary or partial, how many derivatives are being taken, and what are we doing to those derivatives. So now that we know how to classify them, how do we solve them? One common method is separation of variables. Now, that could involve something like this. Let's say dy by dx is equal to y by x. So, on the start, it might be like, how would we integrate y if we just wanted to integrate? But what if we take this dx and put it on this side and what if we had this y and put it on this side and this x and keep it over here and then have the dx go on this side? Well, that would give us dy by y is equal to dx by x, and we would integrate that. And we would realize that the solution to this equation is just y is equal to c times x. Now, that's all good and all, but how do we know that we could use this? this method of just removing stuff to one side versus the other? Well, this is where the chain rule of when I was talking in my previous video what we were doing. When I covered U substitution, trig substitution, and everything else, I talked about moving the du and other stuff on different sides. Now, that all logically follows from the chain rule, and that's something very, very simple that could be solved quite easily using the chain rule, and I'm not going to show it in this video, but you should definitely check out that video to watch that introduction about the chain rule. So, let's do one example, and I think that should be good. Here we have our example. Example 1. dy by dx is equal to 6y squared x. So, without further ado, let's start solving it. Now, what we can do is first, we can bring the 6y squared to that side, or just y squared to that side, and we can bring the dx to the right side. So we get dy by y squared is equal to 6x dx. Now integrating gives us negative 1 by y is equal to 3x squared plus c. Now, taking the reciprocal of that, we get negative y is equal to 1 by 3x squared plus c. And then, taking the negative, we get y is equal to negative 1 over 3x squared plus c. And that's a very simple example. Now, one more thing I wanted to cover in this example is regarding the solution of a differential equation. Do we have an implicit solution or an explicit solution? But what do those terms mean? Well, an implicit solution would be something like this, where you have a constant c that can be determined, or that's just a constant and could associate on different values. An explicit solution would be something like y is equal to negative 1 by 3x squared plus 5. And we would solve this by setting different initial values. Hello everybody, and welcome back to another video on my channel. Today, since we've done a lot of the tests in infinite series and just a lot of the things in general, it's time we do something a little more enjoyable and solve a fun infinite series problem. Now, this is actually a pretty simple problem, but it does require a little bit of creative thinking and slightly disregarding your original intuition about how the problem is. So, I think that's really it. I hope you guys enjoyed the World Cup final that happened last weekend, and let's move on to the video. So, what is this problem? Well, first we have an ant. Now, this ant is on a rubber band, okay? Now, originally, this rubber band is 1 meter long. There we go, that's the rubber band. So, now this ant starts at the beginning. This ant over here, very good drawing. So this is an ant. Now, basically, you can say every second, this ant moves 1 centimeter along this. So in the first second, it'll go here, 1 centimeter along. But then what happens is every second also, this rubber band gets stretched out another meter. So in this first second, this ant goes 1 centimeter, and then what happens is the rod becomes 2 meters, or the rubber band. Now, one thing to keep in mind, as I said earlier, it is uniformly stretched. This will come in very handy later. So, the question is, will the ant ever cross the rubber band? Well, originally you might be like, no, obviously not. We're moving 1 centimeter along, and it's being stretched by a meter, so we're just in an endless race against time, and since it's 99 centimeters more, we will never be able to do it. And if you answered that, you are wrong. Now, as I told you in the beginning, you have to disregard some intuition when solving this problem. So, that's what we're going to do. Let's look at it as facts. So, after 1 centimeter, it'll have moved 1 centimeter, which is 1%, or 0.01 of the rod. So, that's good. That's actually quite good, and it's it's good because we're moving along the rod. Now, it's being stretched uniformly 1 meter. But even if it's being stretched 1 meter, we are still at that 1% mark. So, we're going to have 1 for the first second. Now, for the next second, we cross another centimeter. And that's 1/2% of the total length because it's half of the 1 meter. And again, this is stretched to 3 meters. But that's fine. We still cross another 0.5%. And for 3 meters, we have 1/3. Because when going from 2 to 3, we again have crossed another centimeter. And which is again 1/3% of this whole thing. And then it gets stretched again to 1/4, to 1/5, and so on. So, essentially, we just have this big series over here, and so on, over 100. Now, basically what happens now is, let's write it another way. Well, you can say n is equal to 1 to infinity, this becomes 1 over whatever n is. And we divide this value by 100. Now, again, remember that this diverges because it's the harmonic series. And yes, it does diverge very achingly slow. It will probably take the ants a very, very long time for it to travel infinite distance, really infinite time. So, but all that matters is since this harmonic series diverges, that means at a certain point, it will be at 100 at some time t. And at that point, we will have crossed the whole distance. And the answer to this problem is yes. Yes, the ant will cross, but it will take the ant a very, very, very long time in order to actually do it. But just because it takes a long time doesn't mean it can't or won't happen. So, that's really about it for this video. This is opening up the intuition. I hope it's a more simple and more fun video versus me just explaining another test on top of another test. You actually get to see what it's like to apply infinite series and their principles to problems. So, thank you very much. See you in the next one, and bye-bye.